Railroad tracks seem like some of the most solid and reliable structures ever built. Every day, trains weighing thousands of tons travel across them at incredible speeds, carrying passengers, food, fuel, cars, and countless other goods. To most people, the steel rails beneath these trains appear completely rigid, firmly locked into place, and incapable of movement. After all, they are made from steel, one of the strongest materials used in modern engineering. But hidden within every railroad track is a surprising problem, an invisible force that never stops working. It is a force powerful enough to bend steel, twist entire rail lines, and even cause train derailments. The strange thing is that this force does not come from trains, earthquakes, or storms. It comes from something much more ordinary: temperature. Every material on Earth expands when it gets warmer and contracts when it gets colder. The effect is usually so small that we barely notice it. A metal spoon left on a kitchen table does not appear to change size during the day. A steel beam in a building looks exactly the same in summer as it does in winter. But when engineers build structures that stretch for hundreds or even thousands of feet, those tiny changes begin to add up. Railroad tracks are a perfect example. A rail that is only a few feet long might expand by a barely measurable amount on a hot day. But a rail that extends for miles can grow by several feet as temperatures rise. That expansion creates enormous forces inside the steel. For the earliest railroads, the solution seemed simple. Engineers installed tracks in short sections and left small gaps between them. During hot weather, the steel rails expanded and the gaps became smaller. During cold weather, the rails contracted and the gaps widened again. This allowed the rails to change length without pushing against one another. For many years, this approach worked reasonably well. However, it created a different problem. Every time a train crossed one of those gaps, the wheels struck the ends of the rails, producing the familiar rhythmic sound that many people associate with train travel: clickety-clack, clickety-clack. While nostalgic, those impacts caused wear on both the rails and the train wheels. The ride became rougher, maintenance costs increased, and as trains became faster, the disadvantages became harder to ignore. Engineers began wondering whether it might be possible to eliminate the gaps altogether. The idea sounded almost impossible. If steel naturally expands in the heat, how could miles of railroad track be connected into one continuous piece without buckling? Wouldn't the rails simply twist and bend as temperatures changed? Surprisingly, modern engineers found a way. Today, many railroads around the world use continuous welded rail, where individual sections are welded together into what appears to be one endless track stretching far beyond the horizon. Some of these rails run for miles without a single expansion joint. Yet they survive freezing winters, scorching summers, and the immense weight of passing trains. Understanding how that is possible requires exploring one of the most fascinating challenges in engineering: a challenge involving heat, steel, and forces powerful enough to reshape entire railroad lines. And it all begins with a simple scientific principle hiding in plain sight. To understand why railroad tracks can bend and buckle, we first need to understand a fundamental property of matter itself. At the microscopic level, every piece of steel is made up of atoms arranged in a tightly packed structure. These atoms are never completely still. Even in solid materials, they are constantly vibrating. The temperature of an object is essentially a measure of how much energy these atoms possess. When steel becomes hotter, its atoms gain energy and begin vibrating more intensely. As their motion increases, the average distance between neighboring atoms also increases slightly. The change is incredibly small for any individual atom, but when billions upon billions of atoms expand together, the entire piece of steel becomes longer. This phenomenon is known as thermal expansion, and it affects virtually every material on Earth. Engineers describe thermal expansion using a simple equation. Delta L equals alpha L delta T. In this formula, delta L represents the change in length. Alpha is the coefficient of thermal expansion for the material. L is the original length, and delta T is the temperature change. For steel, the coefficient of thermal expansion is approximately 12 millionths of a meter per degree Celsius. At first glance, that number seems insignificant. But when applied to large structures, the results become surprisingly dramatic. Consider the Eiffel Tower in Paris. During hot summer days, the iron structure can become several inches taller than it is during colder months. Large steel bridges experience the same effect. Without specially designed expansion joints, sections of the bridge could crack or warp as temperatures fluctuate throughout the year. Long oil pipelines crossing deserts and frozen regions must also be engineered to accommodate expansion and contraction. Otherwise, the accumulated forces could damage the pipe or its supports. Railroad tracks face exactly the same challenge. Imagine a steel rail that is 1 kilometer long. If the temperature rises by 40 degrees Celsius, the expansion can be calculated using the thermal expansion formula. Multiplying the coefficient of steel by the original length and the temperature increase shows that the rail will become approximately 0.48 meters longer. That is nearly half a meter, or about 19 inches. For a single kilometer of rail, this might not seem catastrophic. But railroad systems are not 1 kilometer long. Many stretches of continuous welded rail extend for dozens of kilometers. If multiple kilometers of steel all attempt to expand simultaneously, the total movement becomes enormous. Under ideal conditions, the rail would simply grow longer. However, railroad tracks are anchored to sleepers and surrounded by ballast, the crushed stone that helps keep the track stable. These components resist movement. As a result, the steel cannot expand freely. Instead, tremendous compressive forces begin building inside the rail. The hotter the rail becomes, the greater the compression. Engineers sometimes compare this to squeezing a giant steel spring. The energy does not disappear. It remains trapped inside the metal as internal stress. If the rail remains stable, everything functions normally. But if those forces exceed what the track structure can safely contain, the consequences can be dramatic. The steel will attempt to release the stored energy by moving in the only direction available. Rather than growing longer, it may suddenly bend sideways. Entire sections of track can twist into unexpected shapes, creating one of the most dangerous hazards in railway engineering. The question was no longer whether steel expands. The question was what happens when thousands of tons of steel have nowhere to go. By now, we know that steel expands when it gets hot, and that railroad tracks can experience enormous compressive forces when that expansion is restrained. But what happens when those forces become too large? The answer is one of the most dramatic and dangerous phenomena in railway engineering: the sun kink. Despite its harmless-sounding name, a sun kink has the potential to derail trains, damage infrastructure, and put lives at risk. It occurs when temperatures rise high enough that the compression inside a rail exceeds the track's ability to hold its shape. Instead of remaining straight, the rail suddenly releases its stored energy by bending sideways. The result can look astonishing. A section of track that was perfectly straight only moments earlier may twist into a series of curves and waves. From the air, the rails can appear as if a giant hand grabbed them and twisted them into waves. In some cases, the track resembles a giant steel snake lying across the ground. What makes sun kinks particularly dangerous is how quickly they can develop. During extreme heat, rail temperatures can become much higher than the surrounding air temperature. A hot summer day with an air temperature of 35 degrees Celsius can easily produce rail temperatures exceeding 50 or even 60 degrees Celsius under direct sunlight. As the steel heats up, compression continues building. For hours, the track may appear completely normal. Then, once a critical threshold is reached, the rail suddenly loses stability and buckles. To understand why this happens, imagine holding a plastic ruler with both hands. If you pull on it, the ruler remains straight because materials are generally very strong under tension. Steel behaves the same way. It can withstand enormous pulling forces without deforming. However, if you push the ends of the ruler toward each other, something different happens. At first, the ruler resists the force, but eventually, it reaches a point where it can no longer remain straight. Instead of continuing to compress, it bends sideways. Engineers call this buckling. The exact same principle affects railroad tracks. A long rail under compression behaves much like that ruler. Although steel itself remains incredibly strong, the rail as a structure becomes unstable when subjected to enough compressive force. Once buckling begins, the stored energy is released almost instantly, producing the dramatic sideways deformation associated with sun kinks. Railway operators take this threat very seriously because even a small misalignment can have severe consequences. Modern train wheels are designed to follow rails with remarkable precision. At high speeds, a deviation of only a few centimeters can be enough to create dangerous forces between the wheel and the track. If a train encounters a severe sun kink, the wheels may climb over the rail or lose guidance entirely, leading to a derailment. Throughout railway history, several accidents have been linked to heat-related track buckling. As train speeds increase, the risk becomes even greater. A freight train moving slowly may have some chance of remaining on the rails, but a high-speed passenger train traveling at over 150 miles per hour leaves very little margin for error. For railway engineers, the lesson became clear. Thermal expansion could not be ignored, and it certainly could not be defeated. The challenge wasn't stopping expansion. It was controlling where that expansion went. After seeing how thermal expansion can bend railroad tracks into dangerous waves, it might seem impossible that modern railways can safely operate with rails welded together for miles without expansion joints. Yet, that is exactly what engineers have achieved. Today, much of the world's rail network relies on a remarkable technology known as Continuous Welded Rail, or CWR. Instead of installing thousands of individual rail segments separated by gaps, engineers weld the rails together into extremely long continuous lengths. Some stretches extend for several miles, creating what appears to be a single, uninterrupted piece of steel. At first glance, this sounds like a recipe for disaster. If steel naturally expands in hot weather and contracts in cold weather, why don't these continuous rails buckle every summer? The answer lies in a brilliantly engineered system designed to control the immense forces created by thermal expansion. The rail itself is only one part of the solution. Beneath every rail sits a series of sleepers, also known as railroad ties. These sleepers are typically made from concrete, steel, or treated wood, and are positioned at regular intervals along the track. Their job is to maintain the correct distance between the rails and distribute forces over a larger area. But the sleepers alone are not enough. They rest on a thick layer of crushed stone called ballast. At first glance, ballast looks like nothing more than a pile of rocks. In reality, it is one of the most important components of the entire railway system. The sharp-edged stones interlock with one another, creating a stable foundation that resists movement in every direction. When a rail attempts to expand, it must overcome the friction generated by countless contact points between the sleepers and the ballast. The result is an enormous restraining force. In effect, millions of stones work together to lock the track in place. Rather than allowing the rail to freely expand and contract, the system distributes thermal forces throughout the track structure. Engineers take this concept even further by installing rails at what is known as a stress-free temperature. This is the temperature at which the rail contains little or no internal thermal stress. The chosen value depends on the climate of the region. Imagine a railway located in an area where temperatures typically range from -10 degrees Celsius during winter to 40 degrees Celsius during summer. Engineers might install and secure the rail when its temperature is approximately 25 degrees Celsius to 30 degrees Celsius. At that point, the rail is neither significantly stretched nor compressed. When winter arrives and temperatures fall below the stress-free temperature, the rail wants to contract. Because it is restrained by the sleepers and ballast, tension develops inside the steel. During summer, the opposite occurs. The rail attempts to expand, but the surrounding structure resists the movement, creating compression. The key is that both the tension and compression remain within carefully calculated safety limits. As long as the forces stay below critical thresholds, the track remains stable and straight. The beauty of continuous welded rail is that it transforms what once seemed like a dangerous problem into a manageable engineering challenge. Trains can travel more smoothly because there are no gaps producing the familiar clickety-clack sound. Maintenance costs decrease, passenger comfort improves, and high-speed rail becomes far more practical. Every day, thousands of trains safely cross tracks that are constantly expanding and contracting with changing temperatures. It is one of the most elegant and least appreciated achievements in modern railway engineering, a system that quietly harnesses the laws of physics rather than trying to fight them. For more than a century, the familiar image of railroad tracks included small gaps between individual rail segments. Those gaps were considered essential because engineers understood that steel expands when heated and contracts when cooled. Without room to move, the rails could buckle, crack, or damage the track structure. Yet, if you walk along many modern railways today, especially high-speed rail lines, you may notice something surprising. The gaps are gone. The rails appear continuous, stretching toward the horizon as if they were forged from a single piece of steel. This transformation was made possible by continuous welded rail and the sophisticated engineering systems that support it. Modern railroads rarely need traditional expansion joints because engineers have developed ways to manage thermal forces throughout the entire track structure rather than allowing movement to occur at individual gaps. By controlling the expansion and contraction of the rail itself, they have eliminated many of the disadvantages that older track systems once faced. One of the biggest benefits is ride quality. When trains travel over jointed rail, every wheel must pass across countless gaps. Each crossing creates a small impact, producing vibrations that passengers can feel and hear. Continuous welded rail removes these interruptions, creating a smoother and more comfortable journey. The difference becomes especially important on high-speed rail networks, where even minor imperfections can affect stability and passenger comfort. Another major advantage is reduced noise. The famous clickety-clack sound that once defined train travel is largely absent on modern tracks. While many people remember the sound fondly, railway operators are often happier without it. Less impact between wheels and rails means less noise pollution for nearby communities and a quieter experience for passengers. Continuous welded rail also reduces wear and tear. Every impact generated by a rail joint places stress on wheels, rails, fasteners, and supporting structures. Over time, these repeated forces accelerate deterioration and increase maintenance costs. Eliminating most joints significantly extends the lifespan of track components and reduces the amount of repair work required. This helps rail operators save money while improving reliability. Higher operating speeds are another important benefit. Modern high-speed trains depend on exceptionally smooth track conditions. The absence of frequent joints allows trains to travel faster and more safely while maintaining stability. This is one reason continuous welded rail has become the standard for many of the world's fastest railway systems. However, expansion joints have not disappeared entirely. There are still situations where they remain necessary. Steel bridges, for example, can experience significant thermal expansion and contraction of their own. Because both the bridge and the track are moving structures, special expansion devices are often required to accommodate those changes safely. Railways crossing long bridges frequently use carefully designed joints that allow controlled movement while maintaining a smooth path for trains. Expansion joints may also be found in regions with extremely large temperature variations, where thermal forces can exceed the practical limits of standard track designs. Certain complex track crossings, switches, and specialized infrastructure can require additional movement allowances as well. Even in these cases, however, the number of joints is far smaller than it was in the past. The remarkable thing is that railroad engineers didn't defeat thermal expansion. They couldn't. No one can. Instead, they learned how to work with it. Every hot summer day, countless miles of steel rails are trying to grow. Every cold winter night, they are trying to shrink. And yet, trains continue to cross continents safely because engineers found a way to balance these invisible forces. The next time you watch a train disappear into the distance, remember that beneath it lies one of the most elegant engineering solutions ever created. A system designed not to fight nature, but to cooperate with it.